will start now. This will be today, next week, and the week after. It will be the last 3 lectures of this series of lectures about the history of the science of light. And I will devote the 3 last lectures to describe the research in which I have been involved myself. And it's a field which is called, let me try to, cavity quantum electrodynamics. You remember, electrodynamics is a field which has started in the 19th century with the works of Ampere and Faraday, which deal with the interaction of electric and magnetic fields with charges, currents. And it has evolved, of course, in the second part of the 19th century with Maxwell's equation and the recognition that light was an electromagnetic field, and then the interaction of light with matter, which is the field of optics, has been involved in electrodynamics. Then at the beginning of the 20th century, quantum physics has been discovered, and one has understood that the properties of atoms were related to the interaction of electrons with electromagnetic fields. And this is the word quantum in the field. Quantum electrodynamics deals with the interaction of atoms with electromagnetic waves in the framework of quantum physics. And we have seen through Dirac's equation, then through the test of quantum electrodynamics, which had been made by Lamb and by Demelt, who measured the gyromagnetic ratio of the electrons, that this electrodynamics, quantum electrodynamics, is a very powerful and very precise theory which allows to compute the properties of atoms and the energy levels of atoms with a huge precision. I told you that the magnetic moment of the electron was in agreement between experiment and theory with 10 significant digits. So the last term I have to comment is cavity. What it means, cavity quantum electrodynamics? It means that we are studying the properties of atoms and photons, not in free space, as we had dealt before, but inside a cavity, in a box which has reflecting walls. And then we will see that the properties of the atoms are strongly modified. Spontaneous emission can be modified and also can become reversible, because the atoms can emit a photon, and if the photon is confined inside the cavity, the photon can be reabsorbed later by the same atom, and you can have a reversible evolution between the atoms and the photon field. So I will study that, describe that in this lecture. It has started historically in a way which was not predicted. When we started our experiments, we did not have any cavity around the atoms and the photons, and then we understood that the cavity would be a very interesting stage, a very interesting environment for the atomic system, and the experiment were performed in this direction. Then we also noticed that this kind of physics could be very useful to develop the new field of quantum information. You can, in fact, you can code information in atoms which behave as a 2-level system, and when these atoms interact with the cavity field, you have an exchange of information between the atom and the field, and the information stored in the field can be transferred to another atom. So the field can serve as a kind of bus, as a kind of transmitter of information from one atom to another one, and this can be used to perform entanglement between atoms. So this field of cavity quantum electrodynamics has been a kind of testing ground to develop quantum information procedures, and I will talk about that too. The cavity quantum electrodynamics that I will be studying involve microwave photons, but there have been also very nice experiments performed in the optical domain with microcavities, exchanging visible photons between atom and the cavity, but I will not have time to talk about that. I will restrict myself to the microwave domain. In this case, the atoms which interact with the field are Rydberg atoms, very excited atoms, and I will describe to you what it means. I also will discuss in the end the generalization of these experiments to other systems. In the last 10 to 20 years, this field of physics has been extended to deal with artificial atoms. You can have structures which have quantized energy levels much bigger than atoms, for example, superconducting circuits. And when you couple the circuits to cavities, you get exactly the same kind of physics that the one I will be discussing to you. This field is called circuit QED. So it's an extension of cavity QED, and it's very interesting because it's one of the domains where quantum information has been carried further. So in the end, I will talk about that. So how will I divide these lectures? Today, I will give you a general description of cavity QED and talk about Rydberg atoms and microwave cavities, give you just the general context. Next week, I will show you how this can be used to perform entanglement between atoms and photons, and how it can be used to perform what is called quantum demolition measurements of photons. What I will want to stress is that when you detect photons, usually the photons are destroyed by the detection process. For example, the photoelectric effect is an effect in which a photon impinges on a metal or a cathode surface. An electron is ejected, but the photon is annihilated in the process. What we have invented and developed in cavity QED are methods in which you detect the photon, but you don't kill the photon. So the photon is an object, it's something that you observe and can observe continuously as you measure it. And this is very important for quantum information. So this will be in the next week lectures. And the last lecture, I will deal with the generation, the study of what is known as Schrödinger cat states. So these are states which are in superposition of being in different quantum states at once. So it's a kind of illustration of this tale that Schrödinger told about the cat, which interacts with an atom and which is suspended between the dead and the alive state. Here, it would not be a cat, it would not be dead and alive, but it would be systems which are in superposition states and which we try to get bigger and bigger in order to see how the quantumness of the system is perturbed and how it vanishes when the system increases. So this will be a study in one way of the boundary between the quantum and the classical world. And in the end, the last maybe quarter or 20 minutes of the lecture, I will generalize this to circuit QED just to give you a flavor of the idea of what is being done now in this field. So let's start with a general description of cavity QED with Rydberg atom in microwave cavities. So I will start by a kind of historical presentation, talk about early why and how we got into this field, early microwave cavity QED experiments, and we talk about the spectroscopy of Rydberg atoms in free space and in cavities, the first Rydberg atom masers, and I will stress the analogy between these experiments and ion trap physics. And we talked about the physics of ions in traps 2 or 3 lectures ago. I will show you that there are strong similarities between cavity QED and ion trap physics. Then I will describe the atom as a qubit and the cavity field as a quantum oscillator. So in fact, cavity QED is just the physics of what you get when you couple a spin 2-level system to a harmonic oscillator. And these are very simple systems. In fact, in quantum physics, they are the only systems, maybe with a hydrogen atom, that for which you can compute everything without approximation. So when you couple a spin to a harmonic oscillator, you can describe the physics in a very simple and clean way. And so all the quantum effects appear very simply in the theory. And then it's very more difficult to get the effect in the experiments, as we will see, but I will describe how we did it. And we will distinguish 2 regimes of cavity QED. the low Q regime, the regime in which the cavity is bad, quote unquote, which means that the cavity keeps the photons for a short time, and I will explain what short time means, and the high Q regime, which is a strong coupling regime in which the cavity is so good that the photons can stay in the cavity long enough so that you can see coherent interaction between the atom and the field. And so I will distinguish these two regimes. And I will show that in the low Q regime, spontaneous emission rates are modified. And this was a historical development which was predicted long ago. Then I will talk about the strong coupling regime and describe what is called the vacuum Rabi oscillation, the fact that you can have a Rabi oscillation even if you start from vacuum, if the atom is excited at the initial time. Then I will talk about circular Rydberg atoms. These are special, these are very excited atoms which have very long lifetimes and which are very well adapted to this kind of experiments. I will say a few words about the experimental setups, and I will show that cold atoms can be very useful in this kind of experiments, atoms which have a very small velocity. And I will end with describing experiments with photon number states, with experiments which are performed in which the atom interacts with a field which has a well-defined photon number. And I will contrast this with what happens when the field interacts with the field, a coherent field which has a well-defined phase and which cannot have a well-defined photon number if the phase is well-defined, as we have already seen. And I will talk to finish about the collapse and revivals of Rabi oscillations in a coherent field. So first of all, I will, when I started this line of research 30 or 35 years ago, I was primarily interested in Rydberg atoms. It was a time when the lasers had become well developed enough so that you could excite with a very narrow light, very narrow band light excitation, atoms very close to the ionization limit. And you know that if you get close to the ionization limit, the levels are separated by shorter and shorter, smaller energy gap. And so you need very well-defined laser frequency if you want to excite one level and not the next one. So we had these lasers, and we were able to prepare Rydberg atoms. So what is a Rydberg atom? It's an atom in which, for example, an alkali atom, sodium, rubidium, in which you take the valence electron, the outer electron, and you promote it to a very large orbit, which is an orbit which has a very high principal quantum number n. So you end up with a very excited electron, and the remaining part of the atom, which is the nucleus and the other electrons, form a very small ion, and the electron is revolving around this very small ion, which has a unit charge. And so it looks very much like hydrogen. And these atoms have a structure of energy levels which is very close to that of hydrogen. So they're hydrogenic systems, and I have given to you here a kind of classical representation. So you see, you have the core. The core is here with all the other electrons. And then you have an electron on a very large orbit going around. Here I described an elliptical orbit, which has an angular momentum, which is not maximum. The circular Rydberg atom is the one in which the electron is going on a circle, which has a maximum angular momentum. And I will talk about that later. And what we will be interested in mostly is the interaction which makes the electron jump from n to n-1. That is what happens and how you can describe the interaction with the field which brings the electron from one orbit to the next. And this falls in the microwave domain because these levels are very close to each other, and I will give orders of magnitude later. And of course, to perform this excitation, you start from a ground state and you use lasers to promote the electron. So you get a system which looks like hydrogen, which has a very big size and long lifetime, because the electron going around at a large distance from the core has a rather small acceleration at the atomic scale, and it radiates much slower than the atoms which are tightly bound to the nucleus. And so these atoms are extremely sensitive to external fields, to all kinds of perturbation, to microwave radiation, and to interaction with other atoms. So it's a field which has expanded tremendously since we started these experiments long ago. And these Rydberg atoms are useful not only for cavity QED, but for all kinds of studies in atomic physics, which I will not have time to discuss in these lectures. So what we'll be interested in here is to understand how the atom interacts with a single photon, which is either resonant or nearly resonant with the transition between Rydberg levels. And I will call E and G the two Rydberg levels, which are relevant for this transition. I will give you now some orders of magnitude, and I will restrict myself to the circular Rydberg atom. That is an atom whose orbital is a torus around the core. So you see the wave function is localized in a torus going around the core. So it is the closest, the system which is closest to the Bohr atom of the old quantum theory, an electron which moves on a circle around the core. What the main parameter is the size. N is A naught, the Bohr radius, time n squared. And since we will be working with atoms which have a principal quantum number of the order of 50, you see that the orbit size is 0.12 micrometer. So it's an atom which has almost the size of a virus, of a microbe. It becomes something that you could see if it was possible to see it really with a simple microscope. So this is the size. So it's huge. It's about 1,000 times bigger than a ground state atom. Second parameter, which is relevant, the binding energy. And the binding energy is like 1/r. So it's 1/n squared. You know that the binding energy of ground state hydrogen is 13 electron volts. So now you have a binding energy of 5 milli-electron volts for n equal 50, which means that they are very weakly bound, and the slightest perturbation will destroy the atom. So you have to be in vacuum, in a very good vacuum, to avoid collisions with other atoms and to avoid electric and magnetic fields, which will perturb the system too much. Another important parameter is the distance between n and n-1. That is the energy difference between two nearby states. If you divide it by h, you get 2r over hn cubed, because the distance between two n values is the derivative of 1/n squared, which is 2/n cubed. And when you put orders of magnitude for n equal 50, you find a frequency of about 50 gigahertz. So it's why I'm talking about microwaves. It's not visible. It's a frequency which is of the order of the frequency that you have in microwave atomic clocks, for instance. So it's microwave domain. Another interesting parameter is the electric field seen by the electron. This electric field is proportional to 1/r squared, that is 1/n to the fourth power. And when you put orders of magnitude, you find that this field is between 100 and 1,000 volts per centimeter. So it's a field that you can apply easily between two metallic plates. And this means that you can extract the electron with this kind of field. And we will see the method that we use to detect these Rydberg atoms. The last parameter, which is interesting here, is the spontaneous emission lifetime. How long does the electron remain on this state? On a circular state, the electron what it can do is spontaneously emit a microwave photon and cascade to n-1, then to n-2, and so on. They cannot go directly to the ground state because of selection rules. Delta, you can make only jumps by 1 unit of angular momentum, and you can go only for n to n-1 and so on. And the time it takes can be easily estimated. I remind you this formula, which gives the rate of spontaneous emission, It's proportional to the square of the electric dipole and to the cube of the frequency. But the dipole varies as n squared, so you have n to the fourth power here, and omega varies as 1 over n cubed. So omega cube varies as 1 over n to the 9th power. So when you multiply n to the fourth by 1 over n to the 9th, you get 1 over n to the 5th power, which is a huge n to the 5th. It's 50 to the 5th power. It's a huge number. It gives you a factor of the order of 10 to the 10, which means that the lifetime becomes a fraction of a second. I remind you that the lifetime for n equal 2 is about 1 nanosecond. So you multiply this nanosecond by huge factor, and you get a lifetime of 30 milliseconds for n equal 50. 30 milliseconds is a very long lifetime at the atomic scale. So it means that these atoms, you can consider them as stable. During the time of the experiment, they don't radiate spontaneously. So now what about field ionization? How can you understand the process by which these atoms are destroyed when you apply an electric field? You see here the 1 over r Coulomb potential. You have a very deep potential, and you see here the upper state of the condition, and here the n-1 state, which is a little bit deeper in this potential well, and they correspond to slightly different orbit size. When you apply an electric field, what do? You add to this Coulomb potential a linear potential, something which varies an electric field, which gives a slope, a linear slope to the potential. So you see that this electric field will lower the barrier on one side, and if you lower it by the right amount, the upper state will escape, and the lower state will still be bound. So you see that if you adjust well the electric field, you will be able to ionize one level and not the other. So what we do, the method that we use in our experiments is to apply, when we want to detect, we apply a ramp of electric field, which increase in time with a given slope. So at one time, you will reach the ionization level for the excited state, and then later in the ramp, the ionization for the lower state. So you will see two peaks, and the amplitude of these peaks will tell you the probability that you have the atom was in state E or in state G. So it's a very precise and very selective way to detect the atoms in one state or in the other. And this is the only way you can detect the atom. And if you find it in level E, you will call that 0. And if you find it in level G, you will call that 1. So you get 1 bit of information per atom that you detect in these experiments. So what can you do with these atoms? The first thing we have exploited is that we use their huge sensitivity to radiation in order to be able to observe the interaction of single atoms with single photons. And this is not usually what is done in experiments. Here we really can study this interaction in details because we have a huge coupling between the atom and the field. As I will show you next week, we can use Rydberg atoms to detect single photons without destroying the photons, the QN quantum demolition method. And you can also use them to manipulate quantum fields and prepare these fields in quantum states, which are superposition of states with different classical attributes, different phases or different amplitudes. And this is a Schrödinger cat problem. So we will study all this in turn. So when we started, as I told you before, in the 1970s, we used lasers to start from the ground state. This is the case of sodium, which is a n equals 3 s state. With the first laser, you go to the 3p state. And then with the second laser, you can go from 3p to ns or nd states because of selection rules. And you can excite levels very close to the ionization limit. And if you blow up what happens here, you see that you have, in fact, ns, np, nd, nf, and so on, until you get an angular momentum equal to n-1, and this is a circular state. So you see that you have two kinds of transitions that you have to perform to go into the circular state. First, you have to absorb optical photons. These are the lasers. And then you have to absorb microwave or radio frequency photons, because these levels are very closely packed to go to increase the angular momentum and to get into circular state. But at first, we worked with on the low angular momentum states here, with n varying, let's say, from 20 to 50. So we just excited these states, used field ionization to detect them, and you perform a lot of microwave spectroscopy in these states. So if you look into more details, as I told you before, the energy of nn state is R over n squared. In fact, it's not exactly R over n squared. In fact, it's n minus a delta dependent on L. This is a small number compared to n, but this is called the quantum defect. And I will just give you a simple idea of the reason of this quantum defect. This quantum defect takes into account the fact that we are not exactly in hydrogen. When the electron is going around, especially if it is on an elliptical orbit. Elliptical orbit means that when the electron gets close to the nucleus, it is at a distance much smaller than when it is at the largest distance. And so the small angular momentum states penetrate the core. And when they penetrate the core, of course, you cannot talk about hydrogen anymore. So this makes a correction to the energy, which is very well described by this delta L. Maybe an analogy we can make is the wave function of the electron has a wavelength which is modified when it enters in the core, similarly to what happens when light comes into a medium and the wavelength is changed. And this change in wavelength slightly modifies the parameter n and change it into n minus delta L. Here you have the orders of magnitude, and here this is again the orders of magnitude that already discussed for n equal 50. So you see this explains why S and P and D and F do not have exactly the same energy, because the S state has a larger quantum defect than the P state, which has a larger than the D, and so on. And the quantum defects become very, very small when the angular momentum increases, because then you get orbits which do not get close to the core. So the first thing we did was to make a lot of spectroscopy to study transition between these states in order to measure the quantum defects and to try to connect them to the theory. And this is what I show you here. So we did a lot of, this is again the energy levels of sodium or any alkali, and we studied in detail the transitions between all these states to make a kind of chart table of energy levels and to measure in detail the quantum defect. So this is what we did in Paris back in the 1970s. We had colleagues working in the United States, in particular the group at MIT, Dan Kleppner, was working with the same kind of system. And what he did was to study what is called the Stark effect. What happens to the energy levels when you apply an electric field? And so the degeneracy of the states is lifted, and depending upon the projection of the angular momentum along the direction of the electric field, you get different energies. And so they tabulated all these energies. All these are spectra obtained when varying the electric field. They were able to reproduce this kind of diagrams to study what happens in electric fields. And so I show you here the kind of setup that we used in our first experiments. You see, in fact, the experiments are done on an atomic beam. You have a beam of, for example, rubidium or sodium atoms going from left to right. And then we apply a microwave, and the beam is excited by lasers into a Rydberg state. It was a low angular momentum Rydberg state here. And we applied a microwave field to make a transition between two nearby Rydberg levels. And in order to apply the microwave, we had a cavity which was storing the microwave field between a plane mirror here and a concave mirror here. So the cavity was just here to define the geometry of the field, to see when the atoms were entering the field and leaving the field. And after the atom had drifted out, we had a condenser, 2 plates here, and we applied an electric field, a ramp of electric field to detect the atom. And we had here an electron multiplier, which counted the atoms which were detected in level E or in level G. So we did this experiment with different microwaves, and we made a lot of experiments. And one day, what we observed is that even if we didn't apply any microwave, without any microwave, we saw the atoms going from the upper to from the 27 to the 26p state, even if no microwave was applied. What we only had to do was to tune the cavity, the distance between the mirror, to the point where a field could build up, to the point where the wavelengths of the field would match the boundary condition of the cavity. In that case, even without applying a field, the atoms were going from 27s to 26p. This was a maser. In fact, it's the fact that if the atom is excited and enters in a cavity which has the right resonant condition, it will emit photons in the cavity. And this, you see the maser effect here. This is the peak, the ionization peak for the upper state. And in a larger field, you have the ionization peak for the lower state. If the cavity is not resonant, this peak is small. If you put this cavity on resonance, the second peak increases. So we saw this maser effect. And what was surprising is that the threshold for this maser effect was very low. Only a few hundred atoms were enough to observe this. Whereas in an ordinary maser, you need billions of atoms, billions of molecules, because of you need to have this emission occurring faster than the losses of the cavity. So this gave us immediately the feeling that we could get to do interesting physics. And this is a sentence that we wrote at the end of the paper in which we related this maser effect. We wrote that we believe that these experiments open the way to the study of even smaller systems with very small absolute atom numbers. In fact, of course, the goal, the dream was to get to the point where a single atom would go faster to the lower state because of the cavity around it. It is a spontaneous emission of a single atom would be modified by the cavity around the system. And this is what we try to observe. And I will show you how we saw it. Now, what I want to show here is the connection between this kind of physics, atoms interacting with a mode of a cavity field, and the physics that I discussed with you a few weeks ago, ion trap physics, particularly the experiments which were performed in the group of Dave Wynand in Boulder. You see, what we have here, the system we have here is a two-level system, E and G, which is equivalent to a spin, and a quantum oscillator with 0, 1, 2, 3 photons or vibration quanta. In the ion trap system, you have a two-level atom, which is oscillating in the trap. So you have the internal degrees of freedom of the atoms is the spin, and the external degrees of freedom is a number of vibration quanta in the trap. In our case, the atom is a Rydberg atom, which evolves between two nearby Rydberg levels, E and G, and the oscillator is a mode of the field between the mirror of the cavity. So the systems are quite similar. What is the interaction? What is the nature of the interaction between the two systems? In the case of trapped ions, as I described to you before, how do you couple the spin degree of freedom to the oscillator? You apply a laser field which excites a transition on a sideband. That is, you go from E to G, and at the same time, you absorb or emit a quantum of vibration. So you can couple the spin levels to the oscillator level by just using a laser on a sideband. In our case, in the case of cavity QED, it's even simpler. You just need to do is to let the spin couple to the field mode at resonance, and then the atoms will go from E to G and emit or absorb a photon in the cavity, and you have the coupling, natural coupling in this way. But the Hamiltonian, which describes these interactions, are quite similar. And so the physics is also quite similar, although the orders of magnitude are quite different. Another way to compare the two systems is to make this remark. In ion trap physics, you have electrodes which create a trap which keep atoms trapped in this regional space, and you use laser light to manipulate the atoms, to cool them, and to detect them through the fluorescence. So this is the ion trap physics, the kind of physics which was pioneered in Boulder. And at the same time in Paris, we were doing the opposite. Instead of trapping the atoms, we are trapping the photons. So the photons were trapped inside the cavity, and we used a beam of atoms going across the cavity to manipulate the photon field and to detect what happened on the photon. So you see, it's just the two sides of the same medal. Either you use light to investigate matter, or you use matter to investigate the properties of light, and the coupling is quite symmetrical. So in fact, in our experiments, we exchange the roles of matter and radiation. Either we manipulate non-destructively atoms with photons or photons with atoms. Now, I like to say also that this is in vivo physics. Of course, the fact that you detect particles, atoms, is something which has been done well before. You do that in accelerators. But in accelerators, when you detect the atoms, you destroy them. You just look at the fragments. When you use the photoelectric effect to detect photons, also you destroy the photon. Here we are trying to do something much more subtle. What we want to do is to investigate the system, but keep them alive, be able to go on doing the experiment on the same atom or on the same photon over and over. So in this respect, it looks like the thought experiments of the early days of quantum physics, experiments that Bohr, Einstein, and Schrödinger imagined. But they thought that this experiment would be forever impossible. I remind you the famous sentence of Schrödinger saying that this imagining that we can manipulate a single atom or a single molecule will lead to ridiculous consequences. So that's the kind of ridiculous consequences that we try to examine and to study in these experiments. So I will just, now that we have defined the two partners in these kind of experiments, I will just remind you briefly how you describe them in a theoretical framework. I will be very brief on the atom because we did spend a lot of time discussing that already. Our atom is basically a spin. A spin can be described by operators, which are the Pauli operators. And you can define, if you define a direction defined by the polar angle theta and phi, you can define the Pauli matrix, the Pauli operator along this direction as a superposition of sigma z, sigma x, and sigma y. You get a matrix 2 by 2 matrix which describes this component of the spin along this direction. And this matrix has two eigenvalues equal to +1 or -1. These are the 0 and 1 state along this direction, which are linear combination of the 0 and 1 states along the z-axis. So I remind you these formulas. And I also remind you that once you have defined these polar angles, you can represent on a Bloch sphere the tip of a vector on the sphere, which corresponds to all the possible pure states that you can prepare with all an arbitrary amplitude defined by the polar angles theta and phi. And the state plus along the z-axis, we call it 0, and the state minus along the z-axis, you call it 1 in the quantum information language. And the linear superposition of 0 and 1 with equal weights lie on the equator of the Bloch sphere. And I remind you that two orthogonal states are opposite on the Bloch sphere. So these are pure states. We also discussed mixed states which are not pure, and they are represented by Bloch vectors which are inside the Bloch sphere, not on the surface of the sphere. But this is how you describe your two-level atom. Now, what about the field? The field is a quantum oscillator. And as we know, a quantum oscillator is defined by equidistant levels, which correspond to the quantum number 0, 1, 2, 3, and so on. This is a linear, just equivalent to a linear oscillator in a trap. And it is useful to define what are called the creation and annihilation operators, A dagger and A. These are Hermitian conjugate operator, and the A is defined in this way. A acting on N brings you to N minus 1, and A dagger acting on N brings you to N plus 1. So A dagger is creating a photon, and A is destroying a photon. And you have this amplitude square root of N plus 1 is something that we have already encountered, because photons are bosons. If you have already N bosons, it's easier to create an extra boson by a factor whose amplitude is square root of N plus 1. We discussed that in the case of bosons already, and it's the same for photons. And similarly, the Hermitian operator A destroys bosons with a factor square root of N. Now, if you start from an N state and you have acting on it A dagger A. A will bring you to N minus 1, and A dagger will bring you back to N. So A dagger A is an operator whose eigenstates are the N states. So and the eigenvalue is N. So in fact, A dagger A is a number state, is a state which describes the number of photons. And when you write the energy of the field, the energy is given by h bar omega, which is the energy of one photon, times A dagger A, which is N, plus 1/2. The plus 1/2 represents the vacuum fluctuations that we already discussed. So you see these formulas are easy to remember, and they describe what happens when you act on the photon number state with the A dagger or A operator. Now, you have another way to look at this, which is something that you can understand from the analogy with a mechanical oscillator. If you take linear combinations of A and A dagger, you can build the operator A plus A dagger over 2, which you call capital X. And you can also have A dagger minus A over 2 times I, which is also Hermitian, and you call it P. And if you take the commutator of this with that, you find X, and you can compute it easily. In fact, I did not discuss that also. It's very easy to find out that the commutator of A and A dagger is just 1. You just have to act on any N state, and having A dagger minus A dagger A, you will find this. And so from that, you find that the commutator of X and P is just I over 2. And this is the commutation within a numerical factor, because here, with these unities, you have, it's dimensionless. You find the position momentum of a fixitious mechanical oscillator. X and P are just the position and momentum operators of this fixitious oscillator. And they are called, in the context of a field mode, these operators X and P are called the quadrature operators. They are linear combination of A and A dagger, which obeys the same commutation rule as X and P for a mechanical oscillator. And they remind you that for a mechanical oscillator, the ground state is a Gaussian. So the distribution of X values obeys to a Gaussian law. And if you take excited states, you get a Gaussian multiplied by a Hermite polynomial. So you get a wave function which has node between the two turning points. So this is something which would be useful. The last formula that I show you here is how can you define an N state, a state which has a well-defined photon number. That's very easy. You start from a vacuum, 0, and you apply N time A dagger. So A dagger, once it brings you to 1, the second time to 2, and so on. if you apply a dagger to the nth power to 0, you get something which is proportional to n. But of course, since each time that you climb, you multiply by square root of 1, square root of 2, and so on, you have to divide by square root of factorial, n factorial to normalize your state. So this formula gives you the connection between the 0 and the end state. To get the end state, you just have to apply n time the creation operator. So I no longer, my laser is dying, but you see this here. Okay. Now, on this slide, I briefly give a quantum description of the electric field of the vector potential from which the electric field is deriving. So first of all, a reminder about in classical physics. The vector potential is a function which oscillates in time at frequency omega. So you have E minus I omega t and E I omega t here. And you have complex amplitudes, which describe the amplitude of the field, which I will call alpha and alpha complex conjugate. And it can also vary in space. So you have a spatial variation, which describes either a standing wave or a propagating wave. It depends upon the boundary conditions. Once you have found the vector potentials, the electric field is just a time derivative with a minus sign. So you get the same expression here with alpha minus alpha star. When you quantize the field, what you do is just to change the C numbers, alpha and alpha star, they become the A and A dagger operators. So the quantization rule is just to replace the complex coordinates of the field by photon creation operators. You get the vector potential operator here and the electric field operator here, which is proportional to A minus A dagger. And you see that the time dependence has disappeared. So in this representation, the Schrödinger representation of quantum physics, the operators are time independent. What is dependent on time are the quantum states. The state of the field will be dependent on time through the Schrödinger equation. And in the Schrödinger equation, the Hamiltonian will depend on electric and magnetic fields independent of time. So this is this connection. So the quantum state evolves in time according to Schrödinger's equation, which depend upon a time-independent Hamiltonian, which is a function of A and E. So let's now try to describe the vacuum field. In fact, I remind you that when we describe the Heisenberg uncertainty relations, I told you that if a field has a well-defined energy, that is a well-defined photon number, it cannot have a well-defined phase, because this would violate the energy-time uncertainty relations. And this appears here clearly. If you compute the expectation value of the electric field in an n state, you find 0, because the A and A dagger operators are off diagonal. The expectation value of A in an n state is 0, and the expectation value of A dagger in an n state is 0. So we retrieve here the fact that the expectation value of the electric field is 0 in a state which has a well-defined photon number. So what should you do to find non-zero value? You take the square of the electric field, which is the intensity. The light intensity is proportional to the square of the electric field. And in the square of the electric field, you find A dagger plus A dagger A. And this quantity has a non-zero value in an end state. In fact, it's 2n plus 1. So you find that the square of the electric field is non-zero even in vacuum, because if you take n equals 0, you still have this one state here. And so you see that the coefficient here is 0 square is just the intensity of the vacuum fluctuations. And it's multiplied by this function of R, this integral over R, which is a volume. In fact, this is the effective cavity volume, the volume in which the field takes a non-zero value. So you get this expression. And the next step, So you replace the integral of FR square D3R by V, which is the volume of the cavity. And then what you notice is that epsilon naught E square V is just the energy. Epsilon naught E square is the density of energy. You multiply by V, you get the energy. So you have the energy of the field, which is given by this expression. And we know that the energy of a field which contains n photons is just n plus 1/2 h bar omega. So from this equality here, you obtain E naught squared. E naught squared is just obtained by equating these two expressions. And you find that E naught, which is square root of h bar omega over 2 epsilon 0 V, is the amplitude of the vacuum field. And you find again here that you cannot have a zero amplitude because of these uncertainties. Even the ground state has a small residual energy. And if you make the analogy with a mechanical oscillator, this is the ground state fluctuations of the Gaussian function in the ground state of the oscillator. So you have to remind this expression, which is very simple, h bar omega, which is the quantum of energy, divided by 2 epsilon 0 V, take the square root, and you get the amplitude of the electric field in volt per meter if you take the right case. Back. So now let's come back to the structure of my system. You have a two-level system here and a quantum mechanical oscillator. Now, what is the energy of the spin? It's just h bar omega naught over 2 times sigma z. And sigma z, you can write, you can define also the Pauli matrices sigma plus and sigma minus, which is sigma x plus or minus I sigma y. Sigma plus is just raising the spin. Sigma minus is lowering the spin. So they play a role equivalent to A and A dagger for the photons. Sigma plus is creating energy in the spin. A and A dagger are creating or destroying energy in the oscillator. And you have here the Hamiltonian for the two systems. Now, what happens when you couple them? I will just restrict myself to the exact resonance case. So what are the energy levels of the coupled of the two systems together? The ground state is, you have only one ground state, which is the atom in the lower state and the photon in the lower state, G0. But as soon as you put one excitation in the system, you can either have G1 or E0. These two states, if the two systems are at resonance, have the same energy. And so it's a doublet of state, G1, E0. You have another doublet, G2, E1, G3, E2, and in general, Gn, En minus 1. So the levels of the two systems taken together are made of a single ground state and then doublets of excited state with 1, 2, 3 degrees of excitation. Now, what is the coupling between? The coupling is only important between the state in the same doublet, because this is a coupling between states which conserves energy. And we will see the coupling. We describe the coupling very simply now on the right part of the slide. What we have seen classically is that the interaction between a dipole and the electric field, just the product of these two operators. So you have to take the product of sigma plus plus sigma minus here, which is which describe the dipole of the spin. I remind you that sigma plus and sigma minus are off diagonal. So sigma plus plus sigma minus is an off diagonal operator which describes the dipole of the atomic system, and you multiply this by the electric field. So in fact, you get 4 terms. But out of these 4 terms, there are 2 which are resonant and 2 which are anti-resonant. If you take A sigma plus, what it means is that you excite the atom and de-excite the field, or the opposite. These are terms which are important because they conserve energy. The energy is just going from one system to the other. But the terms that I have crossed are terms in which either you excite the two systems together or de-excite them together. And this is heavily non-conserving energy. you lose 2 quanta of energy if you take into account this term. So the quantum physics and quantum mechanics, this term are anti-resonant. And to neglect them is to make what is known as a rotating wave approximation. So you just keep the coupling term, and you find now that if you call omega naught the amplitude here, what is omega naught? Omega naught is just the product of the electric field of the vacuum times the electric dipole of the atom. So you have here a frequency, which is given by this combination, which is called the vacuum Rabi frequency. And you see that the coupling here is omega naught. In the second manifold, it's omega naught square root of 2. Here, it's omega naught square root of 3. And if you go to an n state, it's omega naught square root of n. It's just because of the matrix element of A and A dagger. So you see a very simple coupling. And in fact, what you have to solve are 2-level systems. These are 2-level systems with 1 excitation, 2 excitation, 3 excitation, and so on. And you can solve it exactly because you can diagonalize 2-level system very simply. So I will stop here. And in the second part, we will look into the physics, which can be deduced from